There's an abundance of awe-inspiring sights to see in the night sky. But when I look up, I can't help but wonder, where did it all come from? What really happened at the Big Bang? To really address this question, cosmologists need a quantum theory of gravity. And in recent years, the ability of loop quantum gravity to confront this question has been gaining increasing attention. Loop quantum gravity is an attempt at treating gravity quantum mechanically. Instead of a continuous space-time, which can be divided indefinitely as in general relativity, loop quantum gravity tells us that space-time has a discrete structure, that it's made of individual units which cannot be subdivided, and this has dramatic implications for the origin of our universe. To learn more about it, we visited one of the rising stars in the field, Ivana Guyo, at Cambridge University's Center for Theoretical Cosmology. We also traveled to Florida, where Abhay Ashtekar, one of the founders of the field, was giving a public lecture on the topic.
It's really kind of began when I was in high school, and I grew up in a very small kind of Indian towns. My father was in this civil service, and the British had this tradition that the civil servants were transferred every 3 years, and so we moved a lot, small towns, and then somehow almost, I don't know how exactly this happened, but I got hold of books by George Gamow, and particularly a book which was called 1, 2, 3 up to Infinity, which had things about cosmology in it, and that really fascinated me.
I think since I was a child, I was interested in science and in maths, but I really think that I fell in love with physics, in maths, in high school, when I started to study precise terms, calculus, algebra, mechanics, electromagnetism. I think at that time I felt that my life was engaged with science.
Einstein tried and failed to make his theory consistent with quantum mechanics. So do you find it a bit daunting to do what he and others couldn't do?
Of course. In fact, if I was the only one doing this, I would be extremely worried. But fortunately, there is a lot of people in the field working on the same ideas, the same theories. And I believe that if each of us make a small contributions, all together may solve problems that a single genius was not able to.
Einstein gave us this beautiful theory, which is general relativity, in which gravitation is coded in the very geometry of space-time. That theory is very geometrical. It's very precise. There are very definitive predictions. Quantum theory, on the other hand, uses completely different concepts, completely different ideas. Fundamentally, the theory is probabilistic. There is nothing definite. We predict only probabilities. And rather than being geometric, one uses algebraic methods. So even mathematical tools that one uses are very, very different in the two theories. And therefore, there is a general belief that, in fact, these are two special cases of some bigger, grander theory, which sort of unifies the principles of both of these two theories, and one recovers these theories as special cases. That is why one needs this bigger theory. And it has always happened in physics that once you have such a bigger theory, then it has applications, it has predictions which are far beyond what one could even imagine in the individual theories. And that is why this particular, if you like, chase or this particular hunt for a bigger theory is very exciting. So loop quantum gravity is an attempt at unifying principles of general relativity and quantum physics. And the basic idea is to take to heart the central message of general relativity, and the message is that gravity is encoded in the very geometry of space-time. Now, we know in nature that various fields, like the electric and magnetic fields, for example, fields that describe weak and strong interactions, they are quantum mechanical in nature. Therefore, we all expect that gravitational field is also quantum mechanical in its fundamental nature. On the other hand, Einstein told us that through general relativity, that gravity is encoded in geometry, and therefore, if in fact gravitational field is quantum mechanical, then even the very geometry of space-time should be subject to laws of quantum physics. And this is a central lesson of loop quantum gravity. This is a central viewpoint of loop quantum gravity. Everything is born quantum, and there is no background. Everything is interacting with each other. So it's not that there is actually space and time. There's geometry which is given to you on which things happen. Geometry itself is quantum mechanical, just as things are quantum mechanical. And what the drama that unfolds is subject to some equations which are quantum analogs of Einstein's equations. And these are the basic equations of loop quantum gravity. In loop quantum gravity, one really focuses on space-time structure very much. It's sort of people working in loop quantum gravity came from a general relativity background. People working in string theory came more from particle physics background. So in string theory, at least in the beginning and even now, the emphasis is much more on unifying the interactions, all interactions of nature, and not so much about the peculiar properties of space and time itself. In string theory, higher dimensions and supersymmetry is essential, whereas in loop quantum gravity, it is not essential. Now, it doesn't mean that the two are absolutely incompatible, because it could be, and I think that is the most likely scenario, that whatever the final theory is, it would assimilate in itself some ideas from loop quantum gravity, which particularly have to do with geometry of space-time, how in the real world, quantum world, the singularities of general relativity, the infinities of general relativity are removed. And it would pick up some ideas from string theory, which have to do with unification of all interactions, and some of the very powerful mathematical techniques that have arisen from this so-called ADS CFT correspondence that I referred to before. So in my view, in fact, it is very likely that the final theory will have signatures coming from both these camps.
I mean, the main goal of any theory of quantum gravity is to tell us what happens when the theory of general relativity fails. And this happens when the gravitational field, the curvature of space-time, and the energy density of matter is very high, close to the Planck scale. And in general relativity tell us that at those regimes in the early universe we have Big Bang singularity. But it's important to emphasize that this Big Bang is not a prediction of general relativity. It's just a prediction in a regime in which the theory fails. So it's the result that one gets by pushing the theory beyond its domain of validity. So at that regime, we need to extend general relativity to include the quantum nature of gravity. And this loop quantum gravity, loop quantum cosmology is one of the approaches. And in that theory, we see that in the Planck regime, the quantum effects of gravity totally dominate the physics. And effectively, there is some kind of repulsive force due to the quantum nature of gravity that avoids the Big Bang singularity and replaces it by a bounce.
One analogy given by Martin Boljewald is that of a sponge. A sponge will absorb water poured onto it, but only up to a certain limit. Once that limit is reached, any more water will be repelled. Similarly, in loop quantum gravity, space has a maximum density. Once that density is reached, space becomes full and will repel any excess energy. In the classical model, the universe begins from a state of infinite density and curvature. But according to loop quantum cosmology, the density of the universe has an upper limit. It cannot become infinite. If we were to rewind the cosmic expansion back in time, we would not arrive at an infinite singularity. Instead, as it approaches maximum density, space runs out of room and bounces. A quantum bridge connects our expanding universe to a previous contracting phase. Loop quantum cosmology predicts a big bounce rather than a Big Bang singularity. But why does this prediction arise? Why are the physics of loop quantum cosmology so different from that of general relativity? Well, the answer, of course, lies in the mathematical equations which govern the two theories. So we asked Dr. Aguyo for a layman's guide to exactly how this happens.
What happens here is that when you approach the Big Bang singularity, the energy density grows and goes to infinity in the Big Bang singularity. Essentially, goes to infinity because the amount of matter is the same and the volume of the universe decreases. So the energy density, which is total energy over volume, increases because the volume decreases. So rho goes to infinity and h goes to infinity. That is the Big Bang singularity. In loop quantum gravity, this is the effective equation that one gets. And in that equation, when rho increases, so rho critical is close to the Planck length scale. Rho critical is around 0.41 times the Planck energy density, and this is super high. So when the energy density is much lower than this constant, this term is 0. So we recover the same equation because it's a 1. However, when the energy density is of the same order as this quantity, this factor is important. So we deviate from the GR equation. And at some point, when rho is equal to rho critical, this is 1, 1 minus 1 is 0, and h doesn't diverge. It's not infinity, but it's 0. And this is the Big Bang, because h is essentially a dot, the derivative of a, the variation of a over a. So at the bounds, a changes from big contracting to expanding, so a dot is 0, and when rho is equal to rho critical, we have the Big Bang. So this equation tells us that the Big Bang is replaced by a Big Bang.
The important thing is that this occurs without putting by hand unphysical matter or without adding to the theory some extra boundary conditions. It occurs, it comes out of just the quantum version of Einstein's equations that are used in loop quantum cosmology. And that was a surprising element for all of us when the first papers were actually written. The detailed papers were with these two postdocs, Parampreet Singh and Tomasz Pawlowski. And when this effect was first found, I thought that this couldn't be true in completely general, that without putting anything by hand back at all. This was first done by numerical simulations. So actually, I postponed publication of the papers by repeating the numerical simulations, by varying the initial conditions, by varying the parameters to see if this is completely robust, etc. We postponed it for about 6 to 8 months, and then finally was convinced that this really is there. And since then, this has been verified by, in the simplest models, even by analytical calculations that other people and I have done, that this effect is a genuine effect.
The standard Big Bang model has many problems, which some claim can be resolved if we introduce an extremely brief but rapid period of expansion known as inflation. In inflation, the observable universe doubles in size every 10 to the minus 37 seconds, and these doublings are known as E-foldings. Inflation needs at least 60 of these E-foldings. Some scientists argue that inflation is simply too unlikely. Can loop quantum cosmology help to resolve this debate?
The problem is that the answer depends on what instant of time you actually choose. And if you choose a late enough instant of time, then the probability of inflation turns out to be very small. If you started at an early instant of time, for example, in the Planck domain, then, as was pointed out by Kaufman, Linde, and Mukhanov, the probability of inflation is close to 1. Okay. So the answer seems to depend on how you phrase a problem, basically, and that's a fact. Therefore, to me, the important question is, really, is there a way to choose a preferred instant of time? And now, in loop quantum cosmology, fortunately, there is a preferred instant, and that instant is a bounce. In classical general relativity, there is no preferred instant. And you could say that, well, I choose a Planck time or something. But then, first of all, at Planck time, you should not trust classical general relativity. And why do you choose Planck time as opposed to some other time? It's not so clear. Turok and Gibbons choose late time. And then they get a very tiny probability. But in loop quantum gravity, loop quantum cosmology, since there is a preferred instant, which is really the bounce time, take this initial data at the bounce time And then there is, in fact, a nice finite measure on this space of initial data. And I just ask what fraction, which is induced by the Liouville measure, and I just ask what fraction of this initial data at the bounce time evolve into an inflationary phase sometime in the future, undergoing at least 60 or 70 foldings that are needed. So we're saying, look at the initial data at the bounce, and then you want to know what fraction of this initial data actually evolves or encounters a slow roll inflation with sufficient e-foldings sometime in its future. And then that calculation is completely unambiguous. There's no problem, mathematically well-posed problem, mathematically well-posed solution, and then the answer turns out to be extremely close to 1.
So before 1998, it was thought that the universe might recollapse, but with the discovery of dark energy, it seems that that will not happen. So doesn't that rule out any sort of oscillatory universe that LQC might imply?
Loop quantum cosmology does not predict that the universe will recollapse. What Loop quantum cosmology says is that if the universe were to recollapse in the future, then the end of that collapse is not a singularity, like the Big Crunch singularity that happens in general relativity. But doesn't imply that the universe will recollapse. The reason whether the universe will recollapse or not has to do with the energy content of our universe today and the equations of GR, general relativity, right now. Has nothing to do with quantum gravity. And current observations are compatible with a universe that will expand forever. So in that situation, the picture that loop quantum gravity provides is that the universe started in the past being infinitely big, was contracting until it reached the minimum size. At that time, the quantum effects of gravity were important and avoided the collapse and produces a bounce. And then the universe expands again and will continue expanding forever. So loop quantum gravity is important, close to the Big Bang, and if the Big Crunch would happen, close to the Big Crunch. But doesn't imply that the universe had to recollapse.
Why was the entropy of the universe so low at the Big Bang, Big Bounce? And how could it have been in such a low state if under LQC, the universe has a much longer prehistory? So shouldn't it have built up to intolerable levels in the previous universe?
That's a good question, and it's a question present in many cosmological models. My point of view in the context of loop quantum cosmology is that in our observable universe, in the patch of the universe that we have access, the entropy was reset at the bounds. So in the presence of a phase of inflation in our universe, the size of our patch at the bounds was just a few Planck lengths, around 10 Planck lengths. At those small scales, the effects of gravity are crucial and they are repulsive. They produce the bounds. So these repulsive effects may be able to iron any structure present due to the previous contracting phase. So this quantum, because our universe was so small, our observable universe was so small at the bounds, these quantum effects may wash out any structure coming from the previous branch. In such a way that even when the entropy of the universe is big and there are structures at large scales, at the scales that we can see today, that there was no structure and the entropy was reset at that time.
Dr. Agulló focused on the patch of the universe which is observable today. At the Big Bounce, it was unimaginably tiny, and the repulsive force of loop quantum cosmology drove it to a nearly homogeneous low-entropy state. But what about the whole universe? We asked Dr. Rashtekar to clarify this.
When we talk about entropy, we often just take into account matter entropy and not the entropy due to horizons, if you like gravitational entropy. And see, the notion of entropy has to do with coarse graining, as we saw before. It has to do with not looking at the microscopic states, but just looking at some averaged out macroscopic states up here. Look at the loop quantum cosmology solutions, then in the collapsing branch, just before the bounce, a cosmological horizon develops. And this cosmological horizon grows extremely rapidly and in fact fills the whole universe at the bounce and then disappears after the bounce. So one could be saying that I should use a coarse graining which is associated with this cosmological horizon. In other words, I should only look at the macroscopic state. I should trace over, I should integrate out what is happening inside the horizon. If I did that, then the entropy is increasing very rapidly, and this rapid increase of entropy increase is in fact much bigger than the entropy increase due to just matter. But at the horizon, at the bounce, the horizon engulfs the whole universe, and therefore the entropies, if you like, becomes infinity. And then after the bounce, the horizon has just disappeared. This is a mathematical fact about quantum cosmology. Does not happen in Friedman classical solutions of Einstein's equation, the Friedman model. So there's an issue about how we should phrase this question, whether we should take into account this gravitational entropy which comes due to cosmological horizons. And if we add that, then the mystery disappears, because one is just led to reset the entropy clock, if you like, at the bounce, because at the bounce, the horizon just engulfed the whole universe and then disappeared in the future. There's nothing in the future. There is no cosmological horizon to the future of the bounce. And therefore, we start all over again.
If a quantum bounce replaces the Big Bang singularity, does the idea apply to a black hole?
I think the answer is yes. And everybody in the theory believes that black hole singularities will be also resolved in the theory. The point is that right now there are no precise computations about the details of what happens inside black holes. Big Bang singularity is easier technically because of the symmetries present, but I believe that in the near future people will work out the details of black hole interiors.
As we near completion of this film, there has in fact been further progress. Rodolfo Gambini of the University of Montevideo and Jorge Pullen of Louisiana State University have shown that in the simplest non-rotating black holes, loop quantum gravity does remove the singularity and replace it with a new extended region of space-time.
We came across an old paper by Alan Guth entitled The Impossibility of Bouncing Universes. So how has this idea come back if it was disproved 30 years ago?
The result of Alan Guth was in a specific context and was in the context in which gravity is provided by general relativity, classical general relativity, but they had a peculiar content of matter. And they were wondering if the effects of matter can avoid the singularity. If you look into cosmology, what happens is that GR, general relativity, is not longer valid close to the Big Bang. So one has to generalize the theory to include quantum effects. And when those quantum effects are included, the Big Bang singularity is resolved and the bounce is possible.
It's really quantum geometry that is doing this. I given these talks, in fact, just last month, in February in Boston, in the MIT Tufts seminar. Alan was there, and I mean, they all agree that this is a viable, completely interesting and viable scenario.
We've also heard that contracting universes are unstable and produce messy singularities.
In loop quantum cosmology, people have analyzed more complicated models, not just the simplest model of a spatially flat Freeman-Robertson-Walker. People have analyzed models containing anisotropies. Anisotropies is just a universe in which the geometry and matter has dependence on the direction. It's not isotropic, so there is dependence on the direction. People have considered more complicated models containing inhomogeneities, and in all of them, the singularity does not appear. So we don't believe that messy singularities will appear.
The visible universe is of the size of 10 Planck length cube, and that it turns out that in fact this repulsive force is exactly operating in that domain. It's very, very strong. It completely overwhelms classical attraction. That because of that one is able to not worry about massive things that are happening at much longer wavelength, at much larger length scales, and focus just on this little ball, and that is why we don't have to worry more about these issues so much. We have to worry about these balls of about 10 Planck length size. That changes qualitatively the question. And again, before loop quantum cosmology, the people had, of course, proposed this idea, but the question was, even then, you need some mechanism, even for the 10 Planck length cube ball to become so extraordinarily homogeneous and isotropic. And loop quantum cosmology appears to have, at least qualitatively, a mechanism.
A number of theorists, from Lee Smolin to Nikodem Popovsky, have suggested that black holes can give birth to new universes. So is it possible that the Big Bounce is from a black hole rather than a whole universe that collapsed?
Right. I don't think so, and the reason is basically because of the differences I just pointed out between the bounce and the black hole. For the black hole, most of the energy comes out through this quantum radiation, which initially looks like the Hawking radiation. It looks like a thermal and mixed state, but in fact, the total state is a pure state. It just is well approximated by thermal state in the early times, and so it's quite different from physically. And what bounces is really what is left over, the remnant small thing. Whereas in cosmology, because of near spatial homogeneity and isotropy, the whole thing bounces.
As we don't see inflation in the universe today, the inflaton field driving inflation must have decayed. But in any one half-life, the remaining field, which has not decayed, is undergoing exponential expansion. And so cosmologists such as Alan Guth and Alex Vilenkin propose that inflation must be eternal, creating an infinity of pocket universes. Can loop quantum cosmology determine if this is really the case?
Eternal inflation, they also have to take into account some quantum processes, some tunneling amplitudes, which might, for example, the inflaton is rolling down the potential. This quantum fluctuation puts it up the potential again, and therefore it rolls down again, and therefore causes this little portion of the universe to expand out very much. So these quantum processes are very important for this eternal inflation. What would be good to do would be to actually, in loop quantum cosmology, we have actually a wave function of the universe, and we actually have evolution of this wave function of the universe. Now, so far what we have done is really evolve this wave function until we're reached general relativity era, and says that, well, after that, we can just use classical general relativity. We don't have to use the full quantum mechanical wave function of the universe in the future. And that is a very good practical point of view. Loop quantum gravity or loop quantum cosmology might actually does give you these wave functions, and therefore, if you actually were to evolve these wave functions carefully, you might be able to see whether it is true or it is not true that the inflaton has a large fluctuation and rolls down the potential. It's true that people who believe in eternal inflation seem to think it's obvious that this should happen. I don't have an intuition, so I think it would be good to see if this actually does happen or does not happen.
Can we ever learn what caused the previous universe to collapse, or any other features of the previous universe?
I believe that it is unlikely that we have observational access to the contracting phase of the universe. And the reason is, as I said before, because it is likely that quantum effects wash out information about the contracting branch of our universe.
The New Scientist ran a front cover story recently saying that the universe must have had a beginning. They referred to work done by Borde, Guth, and Vilenkin, and Vilenkin and Matani, but there was no mention of loop quantum gravity at all. Abhayashkar said that this conclusion reached by Borde, Guth, and Vilenkin is violated in loop quantum cosmology. And on a recent TV show, cosmologists at Copeland said that we simply don't know if the universe has a beginning. So which one should we believe?
I think that the result by Borde, Guth, and Vilenkin is very interesting, but one has to interpret it correctly. What they say is that inflation cannot be eternal in the past. Let me explain what that means. What they do was to consider general relativity, so no quantum gravity, classical gravitation, and inflation. In general relativity, Hawking, Penrose, Garrock, and other people came out with what is called singularity theorems. And they say that if the matter content satisfies some conditions, then singularity are unavoidable in the early universe. However, the matter that produces inflation doesn't satisfy that condition. So people were wondering that maybe inflation can avoid the Big Bang singularity. So if you continue inflation in the past, you will never find Big Bang, and inflation can be eternal in the past. Then what Bordy, Vilenkin, and Good shown is that even if the matter during inflation doesn't satisfy the conditions of the singularity theorem, the Big Bang happens. Inflation cannot avoid the Big Bang. So if you extend the inflationary spacetime to the past, you will always find the Big Bang singularity in general relativity. But that doesn't mean that the universe has to have a Big Bang. What that means is that when you get closer to the Big Bang, you have to replace general relativity by a theory of quantum gravity, and this theory of quantum gravity should tell you what happens in the Big Bang. And in quantum cosmology, there is no Big Bang, but there is a bounce. Obviously, there are other approaches that doesn't produce a bounce, produce other results. All these theories are new, and we don't have a complete theory of quantum gravity. So it is natural that the confident answer is that we still don't know what really happened.
These theorems of Vilenkin, Guth, and Bordy, on which much of this discussion is based, they basically assume that the universe was eternally inflating. That is to say, there was no contracting phase in the past. So in quantum cosmology, there is a contracting phase in the past, and therefore the basic assumption of the theorem is violated, and therefore there is a occurrence which is not compatible with the conclusion. I mean, theorems are theorems, but if the assumptions are violated, then the conclusions of the theorem are not true.
Tell us how we can test for loop quantum gravity and loop quantum cosmology.
In general, relating quantum gravity with observations is a very difficult task, and the reason is simply because of the difference between the energy scales at which quantum gravity is important and the energy that we can check in our laboratory. So far, people have checked consistency, or people have tested quantum gravity just by mathematical self-consistency. So the only way that we can hope to see quantum gravity effects is in the universe. People have argued that maybe gamma ray bars are able to provide information. Other people have proposed to observe black hole evaporation. And other people have proposed to see the CMB and the galaxy distribution. From my point of view, I think that the most promising thing that we have is the CMB and the distribution of galaxies. Because we know that the way in which the galaxies are distributed and the inhomogeneities in the CMB were originated in the very early universe. And it is possible that quantum gravity were contributing to that. So this is why the observations by Planck are so important. At this point, so what is really difficult is to disentangle the effects from quantum gravity from other contributions. This is a very difficult task, but I think it's not impossible.
One could say that everything that we are seeing today is actually compatible with the starting at the loop quantum cosmology at the Planck scale. And so we have complete theory from the Planck scale to these 11 orders of magnitude in curvature and density to the onset of inflation, and then from onset of inflation to CMB, and from CMB to the present epoch. So one could say that this itself is every observation we are seeing, if you like, is compatible with loop quantum cosmology from that point of view. But what one would like to see is, in fact, there is some observation which is signature of loop quantum cosmology, which is not seen in standard inflation. Now, so far, this recent work over the last year, I mean, we have been doing it for 2 years. It is a hard problem. We did it very slowly, and the papers were just published in the last few months. So there are 3 papers with Ivan Aguirre that you will see, and William Nelson. And what we have found is that there is actually a very small window in the parameter space for which loop quantum cosmology predictions are completely compatible with the present observations, but would give you some distinct signature from standard inflation for future observations. Basically because we start at the bounds, we have some quantum state, we evolve it to the onset of inflation through these 11 orders of magnitude, and there the state can be close, the quantum state of these perturbations or these fluctuations can be close to what is assumed in inflation, but it's not exactly the same. And because of that, it is sufficiently close that there is no problem with our current observations, but it's not exactly the same. Therefore, it does have potential for having seen in future observations.
It's been suggested that light from a distant gamma ray burst could be affected by the discreteness of space. Assuming that these effects can occur at the scale of the ratio of the gamma ray energy to the Planck energy, attempts have been made to observe them. Some observations have failed to see such a modification, whereas others have claimed a possible detection. But do quantum gravity theories really predict such an effect?
For almost any kind of reasonable thing you see in loop quantum cosmology or loop quantum gravity or anything else, so suggests that it will be at least just probably analogy with condensed matter physics, where there is actually discreteness, and we see that discreteness like in the crystals and so on and so forth, that the effect will be a square of that. And square of that is very, very small. It's true that, gung-ho people have sort of, in loop quantum cosmology and other areas, have often proposed, well, maybe there is the effect of this order, which is energy density divided by the Planck density, which is a small number. And these effects, these results are basically saying that, well, no, there are no such effects. But that doesn't say anything about, these are already heroic observations, and they are very nice, and don't want to take anything away from them. And we want to encourage people to make more and more accurate observations. But if we just go and tell them that, well, what one needs is square, then the effect is so small that nobody will ever look for those effects, so to say.
A number of future space-based missions are being proposed to look for new data on the early universe. ELISA plans to directly detect gravitational waves. The Big Bang Observer is on the drawing board to detect primordial gravitational waves, but this ambitious project requires not 3 spacecraft, but 12. A more realistic goal might be to look for a type of polarization in the CMB known as B modes, which originate from primordial gravity waves. Proposed fourth-generation CMB detectors, such as EPIC and CORE, may be able to find these modes if ESA's Planck mission or other projects do not. So how can data from these missions confront theory with observation?
There is a consistency relation between gravitational waves, how much energy density there is in gravitational waves and how much energy density there is in matter, and the thing that I refer to as spectral index, namely that the energy per wavelength is not the same, is not constant, but it's almost constant, but not quite. And there are some relations between all those quantities. Standard inflation gives you one relation, which is quite robust, but in loop quantum cosmology changes that relation. So if in fact one were to be able to measure these quantities, one would be able to see if in fact this relation holds or does not hold. Again, unfortunately, this is true only for this narrow window of the parameter space, but still the gravitational waves and would be able to shed light on this.
There's been talk that the LHC might be able to make tiny black holes. If it did, could observations of those help us?
Yes, of course. That will be extremely interesting. There are many assumptions on the existence of black holes in LHC. You have to assume that there are extra dimensions, more dimensions than the 4 dimensions that we see today, and they have to have a peculiar geometry. They have to be large extra dimensions. In that case, gravity at large energies may be much stronger than what seems at our scale, and black holes may be produced at LHC. If that is true, that would be great, because we will have black holes disintegrating, evaporating inside our detectors. That would be wonderful.
In March 2013, ESA's CMB probe Planck revealed its cosmology results. The data is plotted on what is called a power spectrum and was said to fit well with simple inflationary models. But anomalies first hinted at by NASA's WMAP were confirmed by Planck. In particular, the left-hand side of the plot at large angular scales showed the most deviation from standard predictions.
At the Planck press conference, Georges Efstathiou of the University of Cambridge said,
I think if I were an inflationary theorist, I would be more happy than disturbed by these results, but we have to be open-minded that there might be new physics involved in these anomalies. And it's perfectly possible from the theoretical point of view that there is exotic physics, that our universe is part of a multiverse, that we can track our universe back through the Big Bang to a previous Big Bang phase.
One can start the computation of where the cosmic structures are coming from, starting before inflation, at the times of the bounds. Follow them through the quantum gravity regime, and then after inflation. And then one can see if there is any correction to the standard predictions of inflation due to the pre-inflationary quantum gravity regime. This has been done, and precise computations of the power spectrum for scalar perturbations and gravity waves are computed, and they in fact say that the predictions of inflation should be corrected at large scales, the left-hand side of the plot. And this is compatible with Planck is measuring. So it's possible that Planck is observing effects of quantum gravity. With the amount of data is not enough to single out quantum cosmology or any other proposals, but it is extremely interesting.
I think that I would like to understand this much better, and in fact, just 2 weeks from now, we have invited. I mean, we're astute enough to do it, a year in advance, so that Charles Lawrence, who is the chief NASA person in Planck mission, so he's going to come and give us 3 talks, and then I would like to understand these anomalies much better. I mean, we had discussions on them, and we realized that there are some basic issues with those anomalies that we don't completely understand. Okay, so therefore I can only answer the question at a rough global level and not anything which is specific. I think it is possible. I think if there is something if we understand those anomalies better, it could be telling us something about the initial state that we have talked about, which is really at the level of the big bounce. This initial state of this 10 Planck length cube thing that we mentioned before, even if you put all these various conditions that I was telling you about before, symmetry requirements and various conditions to tell us what this initial state was, it still gives you some freedom. And if there are anomalies, then it may be that it actually constrains this initial state significantly. There are real anomalies, then that might constrain this initial state significantly. And that would be very nice, because that would give us really insights into kind of new physics. And that will also enable one to make more detailed predictions, because at the moment the predictions are common to this whole class of states.
But so far, the results from Planck are consistent with the quantum cosmology, correct?
That's correct.
Human beings have long sought our cosmic origins, and with modern cosmology and the Big Bang, it seemed like we were close to discovering them. But if loop quantum cosmology is right, the Big Bang is not the ultimate beginning, but rather a transition in a much longer history. So the search for our cosmic origins is not at an end. But perhaps we've opened the door on an exciting new vista.